The artificial intelligence systems generating text, images, and code today are not perfect replicas of the human brain. They are the mechanical solution to a highly specific mathematical optimization problem. The pursuit of that solution began in the 1950s. Almost immediately, the researchers attempting to build an artificial mind split into two fiercely competing factions, driven by very different theories of what intelligence actually is. The first faction championed symbolic AI. They believed the essence of intelligence was reasoning. To them, the mind was a logic engine, processing information by manipulating abstract mathematical expressions and rigid rules. The second faction pursued biological AI. They argued that true intelligence is rooted in perception, not high-level logic. Their goal was to reverse engineer the physical, cellular networks of the brain. This photograph shows Alan Turing, the mathematician and computer scientist who was an early pioneer of this biological, network-based approach before his untimely death. This is John von Neumann, another critical mathematician who aligned with the biological paradigm. He recognized that the chaotic networks of the brain offered capabilities that pure symbolic logic could not replicate. This choice between logic and networks would define the limits of computing for decades. While logic seemed like the more mathematically elegant path, its inability to handle the noise of the real world would eventually clear the way for the biological approach. Symbolic AI operates much like a high school math equation. You take rigid premises, apply strict rules to manipulate those expressions, and derive a concrete conclusion. The fatal flaw of this approach is its rigidity. A system governed entirely by strict logical rules is incapable of processing the messy, analog reality of the physical world, and it completely fails at reasoning by analogy. High-level reasoning is actually a late-stage developmental trait. Human toddlers master complex visual perception, recognizing objects, faces, and environments years before they possess the capacity to perform basic logical reasoning. This exposes the foundational problem of early computer vision. It is mathematically impossible to write a definitive set of logical if-then rules to describe what a bird looks like, whether it's an ostrich up close, a seagull in the distance, or half hidden in a cluttered forest. To solve this, researchers introduced the concept of microfeatures. A microfeature is a tiny, isolated sensory data point, like a curve, an edge, or a shadow. A macroscopic concept, like a bird, is actually a massive collaboration of these microscopic data points activating simultaneously. Deep learning ultimately triumphed by abandoning human logic entirely. Instead of writing rules, engineers built systems that distribute connection strengths across a vast network, mathematically mapping microscopic data up to macroscopic concepts. The baseline input for computer vision is entirely numerical. Computers do not see shapes, feathers, or beaks. They only process a massive array of numerical pixel intensity values, ranging from light to dark. The brightness of any single, isolated pixel tells the computer absolutely nothing about the broader image. Birds can be black, white, or brown, rendering individual pixels meaningless on their own. This animated diagram demonstrates how we extract meaning from those numbers by building an edge detector. We start by isolating a specific microscopic cross-section of an image, two adjacent vertical columns, each 3 pixels high, connected to a single artificial neuron above them. We apply a mathematical weighting to this structure. We assign large positive weights to the left column of pixels and large negative weights to the right column. In a zero-net scenario, if the pixels in both columns are equally bright, they send equal values upward. The positive and negative math cancels out to 0, and the neuron stays quiet. However, if the left pixels are bright and the right pixels are dim, the positive weights dominate the equation. The negative votes are multiplied by small intensity numbers, while the positive votes are multiplied by large numbers, causing the neuron to register a high positive integer. The result of this simple math is perception. The neuron has just successfully detected a vertical edge, where a light area meets a dark area. By simply multiplying pixel intensities by specific positive and negative weights, we hand-wired a mathematical feature detector. We taught a machine to see an edge without writing a single line of traditional code. In a multi-layer network, these simple edge detectors combine their outputs. A second layer of neurons evaluates the edges from the first layer, detecting geometric primitives, like 3 edges sloping downward to form the angle of a beak. That second layer then feeds into a third layer. The third layer evaluates the geometric primitives, combining shapes like a beak angle and a circular eye into a fully recognizable concept like a bird's head. But the variability of the physical world creates an immediate problem. A bird could be an ostrich right in front of the lens, or a tiny seagull far in the distance. The system requires different, highly specific edge detectors for every possible scale, angle, and position. This diagram illustrates the computational wall of the 1970s. To cover all those visual variables and reliably recognize multiple objects, the network would require at least 1 billion individual connection weights. This is a hard human limitation. It would take an eternity for researchers to manually calculate and input the correct positive and negative mathematical strengths for 1 billion distinct connections. For artificial intelligence to actually function, humans had to step out of the loop. The network had to somehow learn to wire itself. The radical solution to this bottleneck was to stop trying to design the network and instead start by assigning completely random mathematical values to all 1 billion connection strengths. This animated diagram demonstrates the forward pass. When an image of a bird is inputted, the random math predictably produces a tiny, incorrect activation level, say 0.01, at the output node meant to represent bird. This is where supervised learning takes over. The system is explicitly told the correct answer is 1.0. This allows the computer to calculate a precise, measurable mathematical error between its random guess and the actual target. You can think of this error as a physical force. Imagine an elastic band attached to the weak 0.01 activation, constantly trying to pull that output value up toward the correct target of 1.0. The core mechanism that resolves this tension is called backpropagation. Backpropagation is a calculus algorithm that calculates the gradient of the error, taking the force of that elastic band and sending it backward through the hidden layers of the network. As this force moves in reverse, it slightly increases or decreases the incoming weights of every single neuron along the path, guaranteeing that the network will output an answer closer to 1.0 the next time it sees that specific image. Deep learning is simply the automated, mathematical minimization of error. Through repeated cycles, backpropagation allows a machine to slowly sculpt abstract concepts out of random numerical noise. The word deep in deep learning is not a metaphor for profound thought. It refers exclusively to this backpropagation process operating across multiple hidden layers of artificial neurons. The architecture of these networks highlights a strict divergence from human biology. A human brain contains roughly 100 trillion neural connections, giving us massive local processing power. The biological constraint is time. We only live for about 2 billion seconds. We possess a massive number of connections, but have a relatively tiny amount of experiential data to train them on. This server room illustrates the exact opposite constraint found in large language models, or LLMs. An LLM might possess only 1 trillion connections, a fraction of the human brain, but it has access to an almost infinite amount of scraped data. Backpropagation perfectly solves this digital constraint. The algorithm is highly efficient at packing massive amounts of global data into a relatively small number of mathematical parameters. Large language models are not mimicking the human brain's structure. They are solving a different optimization problem entirely, using vast amounts of data to compensate for their lack of physical connections. This architecture relies on distributed representation. Neural networks do not store discrete files, documents, or text strings anywhere in their hard drives. Knowledge only exists as the relative mathematical strengths of billions of invisible connections, sitting dormant until a prompt triggers an activation wave. When an AI generates an answer, it is not retrieving data from a database. It is probabilistically reconstructing an output on the fly, predicting the next mathematical weight in the sequence. Psychologists refer to this process of reconstruction as confabulation. Confabulation is a phenomenon studied since the 1930s, where human brains seamlessly reconstruct plausible, but entirely false, memories to fill in gaps. This is a photograph of John Dean, White House counsel for Richard Nixon. During the Watergate hearings, he testified under oath about Oval Office meetings. He didn't intentionally lie, but his brain reconstructed a highly plausible yet factually flawed version of events based on the neural weights of past experiences. This biological quirk applies directly to modern AI. When a chatbot invents a fake legal case or a historical event, it is not experiencing a software bug or a hallucination. It is confabulating, reconstructing the most statistically plausible sequence of words, exactly like a human witness. The exact same mathematical calculus that allows a neural network to brilliantly recognize the edge of a bird's beak is the mathematics that guarantees it will occasionally invent a lie. In deep learning, truth and deception share the exact same architecture.